time derivative of the variable y involved in the equation will be the order of the system. In this case, in this generic equation, the order of the system is n. For this example, it is 1. For this one also, it is 1. So therefore, for causal system, the order of the system, we can say here it is n. So next we will discuss some mechanical systems and their mathematical modeling and their representation using differential equations. Okay, so let us first take an example where, say, this is a spring mass and damper system which is placed on a frame which is having wheels. Like why it is done to have this, we will provide the input u to this platform. That is, we will make a displacement to the platform only, and for that cause we will see what is the effect on this mass sitting on that platform. Okay, the structure is clear to you?
Yes, ma'am.
So my drawing is not that good. You have to bear with it. So we will provide a input, that is displacement to this platform only, and we will record the displacement of this mass. Okay, so can you tell me what will be the differential equation involved? So we will try to write the, using Newton's second law, the acceleration of this mass. So what will be that?
My double dot, I think,
Y double dot, and
plus
that will be equal to,
k into u minus y dot.
so we will write, so this is the direction y we are recording, this displacement y we are interested in. So therefore we will write what will be the
Minus k into
yes,
y dot minus u.
no, for k it will be
Oh,
only
sorry.
displacement of
Y
y
minus
minus
u.
u. Yes,
Yeah, yeah.
thank you. Y minus u, and for,
Minus c.
yes,
Here is a b.
yes,
Y dot minus u.
yes. So it will be y dot minus u dot.
Is
This is the
madam
displacement.
u is the displacement or is the velocity here?
Displacement. You are
Okay.
using u here, so therefore,
Okay. Okay.
so u is the displacement provided to the platform, and we will record the displacement in this mass m, that is y. Is this clear to everybody? So now we can write it as, or let me write it in the way we have in the last, this. Sorry. Is it okay? So can you compare it with the generic differential equation we have just seen?
Yes, ma'am.
So in this case, what are the coefficients? That is, this one is our fu, sorry, f2. This is f1. Do you agree?
Yes, ma'am.
And this whole thing is f0. You can write. This one is our g1.
And
This is g0.
G.
Okay, so G0 and F0 are linear in U or Y or T. Do you agree? These
Yes,
two
ma'am.
are linear, and G1, F1, and F2 are constant.
Yes.
So therefore, the system is linear. Do you agree?
Yes, ma'am.
F1, F2, F0, G1, G0, none of them depends on, none of them are explicit function of
Time.
t. Therefore, this is time invariant.
Wait, yeah.
And what is the order of the system?
Second order.
Acha. So, how many energy storing elements are there in this system?
There are two energy storing element. One is I think spring and other is the damper.
Okay. One is
Spring.
another.
Another is damper, ma'am.
That is the problem. So, we have to see. We have to see that for a mechanical system, the energies.
Energy absorb. It is like
Yes.
dissipating the energy.
Which one?
The damper.
Damper. The
Yeah.
damper is dissipating the energy.
Yeah, but the spring is storing the energy.
Yes, the spring is storing the energy and mass is storing the energy.
Storing the energy. Yeah, the inertia.
Yes. So we are in which form this mass is storing energy? Can you tell me?
Kinetic energy, I think.
Kinetic energy. Why not potential energy?
Uh, Actually, it is, madam, a dynamic system. If we apply the acceleration the opposite direction, then we are converting it into the static system. Actually, it is dynamic. So, in the case of dynamic system, I think the energy will be the kinetic energy, I think.
In case of mass, we generally consider potential energy when there is a movement in vertical plane.
Yeah, there
So
is
in
the
this case, the system is restricted such that the vertical position of the CG of this mass is
constant.
fixed. So it will have only motion in this direction, in this horizontal direction. You agree?
Yes, ma'am.
Okay. So now there is two energy storing elements, that is the spring and the mass. And the order of the system is also indicating the same information. Okay. So the order of the system here is 2. And the order also represents how many independent energy storing elements are present in the system. So in this case, spring and this mass are two independent energy storing elements that are present, and therefore the order of the differential equation is 2. Now the problem comes if we make an arrangement of the spring mass damper systems such that the energy storing elements are not storing energy independently. That is, we have somehow managed the constrained the system such that the motions are not independent. In this case, you see the motion of this mass m is only bounded in this end. It is not bounded in this direction. So therefore, whatever displacement is happening in this direction, the same will be reflected
The
in this
spring.
element. Okay, so let us take an example like this. So by seeing, can you tell me how many energy storing elements are there? This damper is an energy dissipating element. There are 3 springs involved and 2 mass elements.
Yeah.
Do you agree?
Yes, ma'am.
Okay. So in total, how many energy storing elements are there?
Total are 5.
Total 5. Now, by without now see, when I have drawn this system, I have not provided any excitation to the system. True.
Yes. Yes, yes.
So now if I provide a excitation, that is I am providing a displacement at this point. I'll push this mass m1 with a displacement u. Okay. Now what we will, sorry, again that same problem. Excuse me, huh? One second, this pen is not working. Okay. Okay, so if we provide a excitation u in this mass 1, how to see the effect of that excitation? Can anybody suggest? We want to see the effect of that excitation on this structure. So what should we record? What should be our measurement?
The displacement of the mass m2.
So you are assuming that the displacement of the mass m1 you know.
We are giving the initial displacement as u.
Huh? So therefore, what will be the final displacement in m1? That is independent. That is u will be the final displacement of m1. Anybody from mechanical? Oh, who was answering?
Yes, ma'am. I was.
Dipjit. Acha, acha, Dipjit. You are from which department?
I am from mechanical.
Mechanical. Okay, okay. Very good. Then you tell me what are the things that will be disturbed by this input I have provided? That excitation that is given to this system, what are the things it will alter in this system? Should we record only the displacement of M2, or we should also record the displacement of M1?
Actually, it is dependent on both.
Yes. So therefore, this displacement of M1, though you are, in the previous case, why we have arranged this system like this? Why we have provided input in this platform only? Because if we would have taken this input, the system as only the spring mass damper, then if you provide an input to the this mass only, if you provide an input here, so therefore that will be the same as the displacement of the mass.
Yes, ma'am.
Okay, so that that's why we have created a system for which there will be a effect on the displacement occurred in the m, but it is not same as the input provided. Okay, so there is a coupling using this spring and the damper. But in this case, if we directly provide the excitation u to this mass m1, then also there will be different final displacement in this mass, and we will denote it with, say, we will denote the displacement in m1 as x1 and displacement in x2 m2 as x2. Why we are taking these two only? Because we want to write the differential equation, and for writing differential equation of this system, of this mechanical system, we are dependent on Newton's second law. So for writing the free body, from the free body diagram of these two mass m1 and m2, we will get the differential equation related to this system. Do you agree?
Yes, ma'am.
So please write the differential equations related to the free body diagram of m1. So the this is the acceleration involved for mass m1. What are the forces working on this? Should I write the free body? Should I draw the free body diagram, or it is okay? So u1 will be one force working on this m1, one force exerted by the spring k1, another two by k2 and b. So please write the equation.
Equal to minus k into x1 minus x2.
I'll write it. Actually, this is very slow. This system. Okay, this is k1 x1.
Minus k2 x2.
No,
Oh,
okay.
sorry, sorry, sorry.
This
Minus
displacement
minus k2 into
k2 is
x1
equal.
minus x2.
Yes, yes. K2. This is x1 minus x2 of minus
minus b into x1 dot minus x2 dot.
Yes. And there is u.
And plus e.
So this is the free body. This we get from the free body diagram of M1. From free body
Yes.
diagram of M2, I should write this also in. Okay, let me simplify this equation. Then we will go for the next equation. Simplify means in the generic for your convenience, you can compare it with M1. This is M1 d2x1 dt2 plus b dx1 dt plus k1 plus k2 equal to b dx2 dt plus k2 sorry okay, so let us write the differential equation corresponding to M2. This will be m dx2 dt
d2x2 by dt square.
you write down. Actually, I'm facing a problem with this
Okay.
writing pad and this thing. So this is Okay, I'll try to write it here. Huh? M2 D2T, sorry, D2X. Sorry. This is equal to, on this,
Yeah,
the
minus, yeah, K3x2
K3 X2, yes, K3 X2 minus K3 X2, and in the opposite direction it will be
minus
K
K2 into x2 minus x1
X2 minus X1 and minus B X2 dot minus
minus
X1
x.
dot. Okay, so there are,
It will be, I think, x2 dot minus x1 dot.
if this is 2 because
Oh, okay.
this is X2 dot, actually X2 dot minus X1 dot. Okay, so by seeing these two differential equations, can you comment on the order of the system?
It's a fourth order system
How?
because there are two second order equations.
Two second order equations. Yes, so two second order independent equations. That's why this is a fourth order system. But when we are seeing only how many energy storing elements were there, we found there are
5.
five energy storing elements present.
Yeah.
But they are, their interconnection is such that the energy stored in those energy storing elements are dependent on one another. So there are only four energy storing elements, any four you can choose, which will be independently storing the energy. I mean, the values of energy stored will be independent. Okay, why? Can you tell me how, what is the amount of energy stored in this spring, in a spring? What is the amount of energy stored? Or on which this dynamic parameter, that is position, velocity, acceleration, on which one this stored energy will depend?
The displacement will be
Displacement.
Displacement
Yeah.
half
only.
x square.
Yes, so half k into x square. So in case of k1, you see the energy stored is half k1 into
x1
x1
square.
square. In case of k3, it is half into
K into x3 square.
x
So x2 square.
x2 square. So and the energy stored in K2 is,
half K2 into x1 minus x2 square.
so therefore, if once this displacement x1 and x2 happened, then energy stored in K1, if you know energy stored in K1 and K2, then energy stored in K3 is not an independent value. Do you get it? The energy stored in K1 and K2, from the values of energy stored in K1 and K2, one can derive the energy stored in K3. Or from the values of K2 and K3, one can derive the energy stored in K1. So therefore, you can
Yes.
take any two of these three and you will get the information about energy stored in all the three elements. But that is not true. If you know the energy stored in K2 and K3, you cannot calculate the energy stored in M1 and M2. Just for the previous problem, you told me that it is a kinetic energy will be stored in this mass M. No? So in case of M1 and M2 also, there will be some kinetic energy stored. What will be the value of the kinetic energy?
Half m1 into x1 dot square for
No,
the m1.
yes, yes. So that is the half into m1 into the velocity involved for m1, and the velocity involved for m1 is x1 dot square.
x1 dot, yes,
For m2, it is x2 dot square. So if
correct.
you know x1 and x2, then also you, from that information you cannot uh, calculate the energy stored in m1 and m2. You need the velocity information, right?
Yes, ma'am.
So therefore, the to calculate the what is the status of the system, now comes the term state. That is, for this mechanical system, what is the state of the system, you can calculate by how much energy at this point of time is there and stored in there within this system. So how do you know that? From the value of x1, x2, x1 dot and x2 dot.
We have to
Do you
solve the
agree?
differential equations.
Yes.
We have to solve that for the
No,
value of x.
you have to solve that, but you can say that if you know the four states, that is the four informations, information of the four variables, that is x1, x2, x1 dot and x2 dot,
Yeah.
you will be able to calculate the energy stored in the system. Yes or
System.
no?
Yes, ma'am.
Yes. So although there are five energy storing elements, only these four states will be enough to give the whole information about this system. So those four variables are called the, but you can take those four variables as the state of the system. So there are four states involved for this system.
Ma'am, in the previous example, you said that the U was enough to describe the system because it was a, spring mass dashpot. So, can you just explain once more about this? Why the U was not enough in this second
No, I
song?
said, if this structure you see, there is a difference. I have provided this U for this structure. For this structure,
Mhm.
we have provided the U, this input displacement on this platform, not directly to
Mhm.
the M.
Correct.
I was telling that for the next problem you see, I have directly provided input to this mass.
Okay.
So in this
Okay.
case,
Okay.
if we provide the input directly to the mass, it will be enough to, the y will be directly equal to u. Do you agree?
Yes.
So
Yes.
that's
Yes.
why, to make the system have independent displacement, that is independent states, we have provided this u to the platform only.
Got it. Got it.
So in this case also, there were two energy storing elements. One, the one type of energy will be stored that as kinetic energy in the mass m, that will be dependent on y dot, and another will be stored in the spring, which will be dependent on y. Okay.
Yes, ma'am.
Okay, so let us see for this problem. So are you familiar with Laplace transform?
Yes, ma'am.
Okay, so for this previous problem, we have agreed that this is a linear time invariant system. Okay, and we will take Laplace transform of the left hand and right hand side of this equation.
Hmm.
Can we do that?
Yes, yes.
Okay, so what will be the Laplace transform?
M into S square Y. Consider, because initial conditions we are considering 0.
Yes, initial conditions we are considering 0. We will assume that there was no energy stored in this mass and this spring. So therefore we will consider this Laplace transform of this to be m s square this will be m s square plus bs plus k.
Okay.
Yes.
Write it with dotted lines, I guess.
Are you using a board, this writing board?
I'm using a board, and this is working only if I unplug and then plug it back in my USB.
Got it, got it.
It's a very but I came to know everybody is working the same XP pen board, so must be a problem with me only.
You can use Wacom if you want to. Like, it gives good service.
Okay, I'll see. So now if we try to write it in terms of the Laplace transform of the output by the Laplace transform of the input,
Transfer function.
yes, when all other initial conditions are considered to
0.
be,
Zero.
we can then we will have a representation like this. So this is called a transfer function representation. And we can also try to represent this system. See, for this transfer function representation, we are actually taking the assumption that all the initial conditions are zero.
Zero.
Okay. So we can only have a steady state analysis of this system and only analysis of the input to output relationship. If there is
Correct.
initial conditions present, then we cannot analyze, or we cannot uh, have the effect of the initial conditions by analyzing this transfer function. Okay, but for studying the input output relationship of a system, this is a effective mathematical representation. So as we are talking about mathematical representation of a system, then first we are trying to find the differential equation representation of a physical system using the corresponding physical laws. That is, for mechanical system you will use the say for this type of mechanical system we are using Newton's second law. From there we are getting the differential equations involved. So by seeing the differential equation, if we see that it is linear and time invariant, then we can think about this transfer function uh, representation of the system. That is, this is one special representation of special mathematical representation of systems that are linear, time invariant in nature, and this analysis
CISO.
for only LTI system with zero initial condition. So first assumption is it should be LTI, and second assumption is the initial condition will be should be zero. So with zero initial condition. Again, we can have state space representation of a system. That is, just now we have discussed s- the status of the system. We can describe using independent energy storing elements. So in this case there are two energy storing elements, and we will take the variables that are responsible for representing the stored energy of the system. That is, for this case, say for spring it is the displacement of the spring, and for mass it is the velocity involved in the mass. So therefore, if we take the displacement and velocity as the two states, and we try to represent the derivative of the states, the first derivative of the states, in such a way, that is, say this is our y here. So if I want to represent the system in such a form that the state, that is the energy stored in k, if it depends on the variable x1, and the energy stored in the mass, it depends on the variable x2. So what I will try to write is, I'll try to write, say, I'll try to write the system equation with the help of in this format. If I want the do you get it? We are trying to write the system equation, this same system equation, in terms of two variables that represent the internal status of the system. So how this internal status of the system can be described? By the energy stored, the stored energy in K and the stored energy in M. And we have assumed that x1 is a variable which, by knowing which, we will be able to know the energy stored in K. Okay. So in this case, we can assume that x1 is equal to y. Do you agree? The energy stored in the spring K will be proportional to the square of the displacement y. So therefore, the state of the energy stored in the spring will be dependent on the variable x1, which is equal to y. As we know the system, we can now assume that our x1 is equal to y, our x2 is so what will be x1 dot? Actually, in this case, we can assume that x1 is equal to y and x2 is y dot. And we want to represent the system as first order differential equations of these two states. So if I take the first order derivative of x1, that is y dot, as a function of y dot and u. So I can write this x1 dot is equal to actually x2. Do you agree?
Yes, ma'am.
And what is x2 dot? X2 dot means double derivative of y.
Hmm. x1 double dot.
That is x1 double dot, but we want to write it as a function of x1, x2 and u. What is x1? X1 means y, y dot and u. We want to write y double dot. X2 dot means y double dot. X2 is actually y dot. So therefore x2 dot is actually y double dot. We want to write y double dot in terms of the states, that is y, y dot and u. From this equation we can write that. You see, this is y2 double dot, which is a function of this. This will be minus b by m. This is our x1. This is our x2, and this is minus k by m x1. So this will be the state space representation of the same system. Now if we analyze this system, for this system, can you tell me by seeing the differential equations whether the system is linear or not? So we will check the coefficients of the differential equation. So all these coefficients are constant and this is linear. So the differential equation is linear and the functions involved that are not explicit function of time, therefore it is time invariant. Therefore the whole system is linear time invariant system, and we can find the transfer function of the system by taking zero initial conditions. So take Laplace transform of this equation 1 and equation 2, and we can find x2s by if we are interested in this x1 output, then we can also take x1s by us. So x1, if we take x1 as output, then we will get one transfer function, and if we take x2 as the output, From this u we will get another transfer function, but we want to capture the whole dynamics of the system. For if we capture x1 also we will get that, but for in this case we are taking x2 as the output, so we will take the transfer function as x2s by us, and we will get. So the thing is, what I am trying to say is, if you capture x1s by us also, you will get a transfer function which will have a denominator polynomial, where the the polynomial have a order of s to the power 4. S to the power 4 will be present in the denominator. So let me write this one. So we'll have m1 s square plus bs plus, from equation 1 I am writing this, and from equation 1 I can write, actually if you try to derive this equation, you take Laplace transform of this. So from here what we will get, you will get x1s, the relationship of x1s with x2s and us, and from this equation we will get a relationship of x2s with only x1s. For equation 2 there is no involvement of input u. Do you agree? So from this
Yes, ma'am.
second equation you just equate, you find the ratio of x1 and x2 and you replace this in this equation, and then you will get this uh, the transfer function what I am writing. Okay. This is m2 square plus bs plus k2 plus k3 minus this bs plus k2 whole square. I have this term bs বাবা, এটা আবার কাজ করবে না। ওকে, so this is bs plus k2 whole square, and in the denominator, numerator, it will be bs plus k2. This is u x2s u2 x2 transfer function, and if we take the denominator will be same, that is the denominator will be same as the previous one, only in numerator it will be m2 a square plus bs plus k2 plus k3. Okay, the numerator will be only different, denominator will be same. Okay, so if you see the denominator of the transfer function, this is a polynomial of s, and the degree of the polynomial is, highest degree of the polynomial is 4. This is s square into s square. Therefore, there will be, this system will be fourth order, and the differentiate, this transfer function will have 4 poles, and for this x1 to u transfer function we have 2 zeros, and for this x2 to u transfer function we have 1 0 involved. Next will be a cart inverted pendulum system. For today we will just describe the system. I think some of you will be familiar with this system. Have you seen this kind of system? So this is a trolley or cart which is wheeled, and on that there is a pendulum that is hinged in the point P. Okay, so for the mass of the pendulum, that is here it is shown to be working on the CG only. So this is the CG of the pendulum, from where, say, let us assume the mass of this pendulum is small m, and from the CG of this pendulum, a mass, the weight mg is shown to be working downward. Okay, and the length of the pendulum is 2L. Therefore, the position of the CG is in the middle of the, say, this is assumed to be a uniformly distributed mass. So therefore, the CG is considered to be at the midpoint. So the distance of the CG from point P is small l. The angle at which, so this angle, the angle at which this pendulum is bent, this is this at point P, it is hinged. Okay, so it can freely rotate about the point P. Now, if we provide a displacement in the cart, that is, you see the arrow U. So if you provide a force, we will disturb the cart. So therefore, this pendulum will be rotating about the point P. Do you agree?
Yes, ma'am.
Okay. So can you tell me what are the 2 points, or what are the values of theta for which we will be able to acquire a force equilibrium? So the mass mg is working downwards. So is it possible to have this pendulum to be at angle theta equal to 0? Have you ever tried to balance a stick on your finger, or balance a pen on your finger? So for balancing a stick or a pen on your fingertip, you have to always move your finger. No? If it
Yes,
if
ma'am.
if it is falling away from you, you just have to uh, move your fingertip away from your body, and if it is falling towards you, you have to move your finger towards you. So the same thing, this problem is a benchmark problem of control, where the model is actually directly applicable to missile launching, overhead crane system. Some of you may have seen Segway personal transporters in uh, this airport, or museum, or some other places. Segway transporter, or this personal transporter systems. The principle of these are also same to this inverted pendulum system. So here our objective is, so what we are trying to do, we are trying to get a mathematical model for this system, where the input force or input displacement will only provided on the cart, and the pendulum stick is to be balanced at the pendulum stick should be at the inverted position, that is at theta equal to 0. So for that, we should have the mathematical modeling of this system, mathematical model of the system. And for that
Yes.
purpose, we should, what is the relation between this, why this cart movement and the pendulum movement is related? Because of the hinge point at P. So we should have the free body diagram of these two separate bodies, that is the cart M, cart with mass capital M and the pendulum with mass small m. So here we are assuming that from this point O, that is the reference frame is hashed, and from the reference frame we are assuming the point P is at a distance small x. Therefore, the CG of this pendulum is from the reference point. What will be the location of the CG? The location of the CG of the pendulum has two coordinates.
X plus L sin theta, I think.
So the vertical coordinate is x plus L sine theta.
Horizontal coordinate.
Sorry, horizontal coordinate, and the vertical coordinate is L cos
Okay.
theta. Okay. So therefore, why we are considering this x cos theta? Because see this cart, the cart is actually restricted, so there will be no vertical movement of the cart. So we are assuming this position to be 0. Therefore, the y coordinate of the CG we can consider it like this, and the x coordinate of the CG we can consider it like this. Okay, so now if we go for the free body diagram, so if we try to draw the free body diagram of this, what we will have at point P, there will be two reaction forces,
Yes, ma'am.
one horizontally, one vertically. Okay, so let us assume this to be V and H. Okay, so this pendulum is moved a little bit so that these two are in the same figure. We have shown the free body diagram for both the bodies. So if we now try to write what are the equation of motion for this cart with mass capital M, what are the forces acting on this cart? The vertical force V will be balanced with this reaction force on the wheels. So we are not concerned with that. We are only concerned with the applied
Right.
force U, the horizontal applied force U, and that is balanced with H.
The
And
horizontal.
for the result, with the resulting force of these two, the cart is moving. So we can, from the Newton's second law, we can write M dx2 d2x dt2 is equal to U, the input
My
force, minus
H.
capital H. Yes. From the free body diagram of this pendulum, so for the pendulum, how many equation of motions will be there? First, you tell me how many energy storing elements are there in this system?
One is the card, that is the mass
Mm-hmm.
of M,
Huh.
and there is a pendulum, that mass of M, small m.
Okay, okay. And in the pendulum, energy will be stored in the pendulum, that for the there will be motion on this xg. In the previous slide we have written the location of this the CG, that is a vertical and horizontal position. Now, so if this rotates about P for application of the force, then the xg and yg both will be changing dynamically. Do you agree? Do you agree? So we need to write that equation
Yes, ma'am.
of dt2, that is xg, and with yg. Do you agree? So please tell me what will be this with xg, what will be there in horizontal direction?
Yes, the small, the capital H.
Capital H only. Okay, so let me write it in a proper way. That is xg is actually d2 dt2 x plus L sine theta. And for the vertical direction, we will have another equation. For horizontal acceleration, this one. For vertical acceleration, we will have L cos theta, and that is dependent on V minus mg.
Yes, ma'am.
Any other equation?
If we take the moment equation at the hinge
Yes.
point,
Yes. So there is actually the pendulum is rotating theta amount about this point P. So this V and H forces, because of this V and H forces. So if we take the moment, we will get I theta double dot V L sine theta VL sine theta is in clockwise direction or anti-clockwise direction?
clockwise direction,
Clockwise direction.
and minus HL cos theta.
Minus HL. Very good. Okay. So we will simplify these equations. These are the equation of motion. And now can you tell me whether this system is linear or nonlinear by seeing the differential equations involved? What are the, can you tell me what are the energy storing elements? You already told me that this is the mass capital M and the mass small m are the energy storing elements. Right. So what are the variables based on which the energy will be stored? Say for capital M, the energy stored will be dependent on the velocity involved. That is x dot. Do you agree?
Yes, ma'am.
What will be the energy stored in the pendulum?
It will depend on the value of theta.
Value of theta. So therefore, there are two variables we can take as measurement. So whether the differential equations are, so the coefficient of the differential equations, like if you expand this equation, say the first equation, this is equation 1. If you expand this equation, you see the coefficients of the differential equation are
M mass.
no are the linear and constant
Yes.
kind. Now if you see equation 2,
अबे আমারটা কি প্রবলেম
will be it will be m double derivative of, there will be one term L sine theta. If you expand
Yes.
this, you will get m double derivative of x plus ml double derivative of sine theta.
Yes, ma'am.
What will be that? This will actually result in nonlinear function
Linearity.
of theta.
Theta.
No, so therefore the whole system, if any one of these functions involved with this differential equation is nonlinear in nature, then the whole system is in nonlinear
No
nature.
linear.
Okay, so for this sine theta and cos theta terms present in the differential equation, the system is actually nonlinear in nature. So if you want to find the transfer function of the system, then we have to linearize the system at any operating point. Okay, we have to choose for this whole nonlinear system, we have to choose a operating point where we will, around which we will linearize the system and find the linearized model. Okay, therefore from this model for today we will conclude here. So we conclude that the system, this cart inverted pendulum system, is nonlinear in nature, although it is time invariant. Do you agree?
Yes, ma'am.
The system is time invariant but nonlinear in nature. So therefore if we want to find a transfer function model of the system, we have to linearize it somewhere. So in the next class we will linearize it at 2 points, which are a natural equilibrium of the system. So we'll find the natural equilibriums of the system, and on those natural equilibrium points we will try to linearize the system and find the transfer function of the system. Okay.
Okay, ma'am.
Okay, so if you have any question you can ask, otherwise we will end the meeting here.
What are the significance of poles and zeros?
Okay, so see, if you see the transfer functions, say let us go to this. So these are names of the, say, when we are talking about transfer function, that means you are having this ys in terms of us, and this is obviously will be two polynomials involved. There will be a numerator polynomial
Yes.
ns and ds. So zeros means the roots of this ns polynomial. So zeros are roots of ns. Why these are called zeros? But from the name itself you can see, if on the values of the roots of this ns polynomial, the value of the transfer function itself will be 0.
Yes.
Do you agree? So
Yes,
that's
ma'am.
why these are called zeros. And at the value, and what is poles? Poles are the roots of ds. So if you take the values, the roots of ds, if you put the value of s in this transfer function, what will be the value of the transfer function in that case? Say, let us
Yes,
take an example. Say we will take s plus 1 by, sorry, one second. So let us take a transfer function s plus 1 by s plus 3 s plus 4. Okay, so if you see the whole of the s plane, where is the 0? What is the
That is
0
equals to -1.
of -1? So at point -1, what will be the value of the transfer function?
0.
It will be 0. So if you take any point in this S plane, this is our S plane, that is, this is imaginary of S axis and this is real of S. So in the S plane, the transfer function will have, for each and every value of S, the transfer function will have some value. Do you agree?
Yes, ma'am.
At the values called zeros, you will have, the transfer function will have value 0. And
Yes.
at poles, it will have value, say at -3. What will be the value of the transfer function? Can you tell me? At -3?
1 by 0 is infinite, I think.
So it will be a, so if we try to represent, so in 3D, if you try to see, it will be a pole when an infinite amplitude point. There will be a shoot at -3. Do you agree?
Okay.
So that's why it is called poles. So at -3 and -4, the transfer function will actually have shoots. Imagine S plane, and in the 3D towards you from the screen, you imagine that value of the transfer function is plotted.
It will act like an impulse function, like.
Yes, yes. Like impulse means there will be a shoot when the value is at a very far, when a very high value, or this is tends to infinity value. So therefore, this will look like a pole. So that's why
Okay.
the name pole comes. So what is the significance of poles, that we will see? We will see afterwards. Okay, why the names are like this, that you can understand from here.
Okay, ma'am.
Okay. So should we end the meeting? Any other question? Okay then. Good. Yes. Okay. Okay.